There's two diagrams, one for exothermic and one for endothermic. We briefly covered this yesterday. This is, I don't know what's going on with my tech today. It's being, it's not green, it's fadey, stupid bulb thing.
Normally, my teacher last year would just like turn it off.
I did, twice.
Well,
Guys, are y'all gonna make it? Are you? Okay, good job. All right, so I'm just gonna continue to write and y'all are just gonna have to deal with it.
well, I don't know what you're
Fine. This has been happening all morning. It's really starting to frustrate me. Very frustrated.
You got it.
Did you just say you believe in me? Great. I'm getting patronized by a 16-year-old.
You can do it.
All right, potential energy diagrams. Here we go. We talked about these briefly the other day, that the energy diagram starts somewhere on the y-axis, increases to a hill, and then drops below where it began. That's exothermic. What we didn't do is label where everything is. So this part that I picked, this is the potential energy, because this is potential energy on the y-axis. This is the reactants. Potential energy here. Products, potential energy here.
Just so you know.
Is this your fault, Caleb? Have you been? Caleb, I'm a little disappointed in you. I thought you were better than this. Fathers, mothers, cats, and hamsters.
That's a new one.
I'm super frustrated because y'all really need this time. All right, we'll label the beginning of the graph reactants. Ah, there it goes. The end of the graph products. The top of the graph is activation energy, and we'll talk about that. So if your reactants are A, B, and C, D, just randomly, and your products are A, D plus C, B, activation energy is at the top. Activation energy.
That was aggressive.
It's fine.
Well, sorry.
And then over the reactants are A, B plus C, D, like a double replacement. You know what? Let's just do this. Yes.
All these recording people are gonna be like, what's going on?
What is going on?
It's good for your time to get it.
All right. Let's do it like this. So you have right here, AB plus CD makes AD plus BC. So those are your products. I've just randomly picked a double replacement reaction. It could be any reaction that you've studied. Activation energy. On top of that, what is going on? We talked about it yesterday. Can you use more words?
Separating and then
Okay, good. So at the top, what's going on are the reactants have separated. Remember, you have to break those bonds first before you can reform into new bonds. And so in this particular case, this exothermic case, the potential energy of the reactants are here, wherever here is. It takes that much energy to break all those bonds, but you get all of that energy back and more with new, more stable products. Now, what? No, it's A, B, C, D broken apart. Yeah,
what is the top of the?
A, B, C,
No,
D
no, the thing under that.
broken apart, activation energy.
I can't see it. It's tiny. It is very tiny. You should just zoom in.
Right here.
Oh. Ah.
Okay, and then the bottom graph is exactly the same,
Yeah.
except that the products end up higher than the reactants.
Can I ask you a very,
Maybe. I can't guarantee that I'll be pleasant when I answer it.
so you know where it says potential energy on the top one?
Yes,
And like at the beginning of the graph, there's like little like,
Yes.
What is that?
I will get there. Hey, there it goes. Yeah. Okay.
Oh.
So I'm going to go back down to the endothermic in a second, but here, remember when you're calculating delta H and you get either a negative or positive number, what you're calculating is the difference between here and here. If it's a negative number, that means that your potential energy has dropped. You have released energy, exothermic. As opposed to endothermic, which is essentially exactly the same thing, but opposite, sort of. Most of it's the same. Your reactants are in the same place. Your activation energy is in the same place. All those broken up molecules are in the same place. Your products are in the same place, but the reaction curve stops above where it started. The top one's a negative delta H, this one's positive. Not bad. What is it talking about when it talks about potential energy? It talks about literally the energy that's stored in those bonds, trapped in those bonds. Why do both of the graphs have this little hill at the top? Because all reactions, no matter if it's exothermic or endothermic, have to have a kick to get it started. So the classic example is something like a match. You have fuel and you have oxygen right here. You know, we have oxygen in the air, waving it around. Why is it not catching on fire? Because I haven't done this to it. Here's my fuel and my oxygen. I have to give it some energy in order for it to go. It's going to be exothermic, I know, because it's going to be combustion. So once I get it to go, it'll release all of that energy and then some. It'll continue on its own. But I have to give it a little bit of a kick to get it started. Once it starts, it can go on its own. Okay. So that's what activation energy is. No matter what reaction you have, you always have to provide that little kick to get it started. Sometimes the kick is so small, it's enough just to be at room temperature. The ambient air gives it enough energy. The ambient temperature gives it enough energy to be able to go. Sometimes it requires a lot of activation energy. So this hill can be really tall or really short. Yeah.
The activation energy, was that the like heat over the yield sign that you were doing?
Okay, so the question is the activation energy the heat over the yield sign when we were doing those reactions? You know, you had like an arrow, A and B over here, and then you had an arrow, and then you had something written over that arrow? No. Activation energy is required for all reactions. That extra information that's written over the arrow is specific to that reaction so that you know what you need to do specifically to get it going. So even though all of them require this, some of them literally, if it goes on its own, some of them just putting them in the same area together, the room will have enough energy to get it going. So that's why when I dropped my zinc and my hydrochloric acid and it suddenly started bubbling all by itself, you didn't see me having to warm it up or do anything like that. There was enough energy in the room to get it to go. But some require quite a bit more, like that match required quite a bit more energy. So in that case, if I wanted to write that one out, yeah, over the arrow, I would put something like heat or friction or a catalyst, something like that, so that the reader would know how to get it started. Good question. Yeah.
So for the endothermic, is it the same exact like kind of like double replacement kind of problem?
Well, okay, so yes, but it doesn't have to be double replacement. I picked double replacement because it's easy, but it can be any reaction. A plus B is equal C D, yeah, and then it rearranges on the other side. Other questions? Yeah.
Can you scroll up?
Oh, my cat, it was literally just there.
No, it was like a part.
Cats.
Thank you.
Oh my gosh. Okay, we good?
Yeah.
Next page.
7?
No, 59 and a half. Yeah. Okay, entropy. This looks terrifying. It's not that bad because we don't put math in it. We used to. If you were an academic, if you were in AP, there'd be tons of math with it. It's really not that hard. It's just annoying.
Cool.
There was supposed to be delta S here for entropy. So sorry about that. It's the same thing as disorder. Okay, so sorry for these being kind of backwards. I was half asleep when I wrote these this morning. The second law of thermodynamics says things in nature naturally proceed to a state of greater disorder. And you know that just from looking at your room. I mean, you really have to put in energy to get your room back in order. You just kind of don't for a while, and it looks like your room, which is probably better than mine. Kitchens are the prime example of this. You walk into a kitchen and it's nice and sparkly, but you let it go for a while and you have dishes everywhere and splotches on the ground. You have disorder. It just kind of happens naturally. It happens in chemistry as well. An positive entropy means that you are going to greater disorder. That's spontaneous. That happens on its own. That's your room. A negative entropy is non-spontaneous. That is you cleaning your room. Non-spontaneous, it requires effort. Physical processes, and this should have been a little bit different, but again, I was pretty asleep when I wrote this. Low disorder, low entropy to high entropy, the phases of matter, solids have the most order, so therefore the lowest disorder, the lowest entropy. Then liquids, then aqueous solutions. I need to ask you if you remember that. Then gases. And then fewer moles or greater moles, ignore that for now, because that needs to be in chemical processes. So we'll put it down there when we get there. All right. Let me see if I can fix that. Hang on, don't write yet. I mean, do write, but don't write yet. I know you're working, just work faster, please. Okay, here we go. They've been fixed. They're messy, but they've been fixed. All right, what are aqueous solutions? Dissolved in water, good. So in order of low to high entropy, solids, liquids, aqueous, gas. So, for example, if you have, and before you write, I want you to listen. CO2 solid sublimating to CO2 gas. You're going from solid to gas, that's an increase in entropy, an increase in disorder. Going from solid to aqueous, increase in disorder. Flip them and you get a decrease. Yeah? All right. Okay. Now moving on to chemical processes. All right, exothermic and endothermic. Exothermic, you have an increase in disorder, an increase in entropy. Endothermic is a decrease in disorder. Endothermic is more orderly. Entropy. Even though this sounds like enthalpy, what we just did on MathWise yesterday for homework, allegedly, this is different. This is entropy. Yeah. Okay. So that's a great question. How is exothermic more disorder? It makes more sense to me to think of endothermic first, and then exothermic would be backwards. So I'm going to explain it in that way. Endothermic. Think of the curve, right? And then think of cleaning your room. Endothermic, you're having to put in a lot of energy to get it to go. You don't get a lot of energy back. So you're endothermic, you're decreasing disorder. You're making it more orderly. That's endothermic. Exothermic, it just kind of happens on its own. You still have to get it to go, but then once it goes, it gives you a lot of energy. You are increasing disorder. Remember, disorder is what happens naturally. Did that help? Yeah, it's hard because you're talking about disorder, which is a negative thing in your brain, right? And so you're like, oh, it's a positive entropy. Wait a minute. No, you're increasing its disorderliness. It's happening naturally because that's what nature wants to do. If you're decreasing entropy, you're actually making it more ordered. You're going against what nature wants it to do. You're going to have to put in energy to do that. Did that help? Hurt? Need more questions? Okay. Moles also affects it. So if states of matter are tied, you can look at moles. Low entropy, fewer moles. High entropy, greater number of moles. So we're talking about more and greater and less, less and greater on each side of the reaction arrow. So for example, these two both have an increase in disorder. See if you can see why before you copy it down. Yeah, give me a second. I want you to see if you can see why. And then I'll scroll back up and let you write. States of matter are tied. Gases on both sides of the arrow. So that's not going to help you. But if you look over here, not balanced. Don't be all. Hang on. Got to get it balanced. Somebody balance it for me so I can check it. Yeah. Oh, it's not. There we go. Okay, but it's still not balanced. So y'all balance it with me, would you? Oh man, if you got that right, you need to go do something else with your life. That's kind of impressive. All right, so I've got 4 oxygens, 8 oxygens, 8 oxygen, yeah. So 1, 4, 2, 4. That's an L. So 1, 4, 2, 4.
So 1, 6,
Yeah,
1, 4,
2, 4. Okay. So let's change this from liquid to gas, and that'll make this an even better question. So the C2H8, change it to gas. And that'll make this an even more cut and dried question. Change the C2H8 to gas. So it's gases all the way through. So change this to gas, and then it's 1, 4, 2, 4. Oh, my cats. I know. I'm working. Calm down. Oh. Okay, now it's fixed. I don't understand how I can fix it on my thing, send it to the cloud, have it downloaded instantaneously to here, and I can't get my Apple TV to sync literally like 4 feet away. It's very frustrating,
It's fine.
but I'm fine with that.
All technology.
Okay. So see if both of these make sense. And I'm meaning that in a no, really, see if they make sense manner, because again, this day has not gone well. Yes?
I have a question.
Is that why your hand went up?
Yes. Oh, okay. Yeah. How do you know if like something like this is extra or endo?
Oh, great question. How do you know if something like this is exo or endo? You'd have to calculate delta H. And I have to give you those delta H values so that you could. You'd have to do what we did yesterday that you didn't do for homework.
Wait, it's hard.
Well, if I give it to you,
Well, if you have a balance of
you should be able to predict whether it's exo or endo by entropy. Yes. How much? No, you need delta H for that. What else? You have a practice, it's very simple, it's very straightforward. There is one that you can't tell. It's not a fair question. On the front, there's one where you can't tell. So see if you can figure out which one that is and put can't tell. The key is up here. Now, hear me. You need the back of the enthalpy practice from yesterday. It is on Canvas. I will print it out for you as well, so you'll have it tomorrow. You'll have today and tomorrow to finish working on both of those. So if you don't feel like doing it for homework tonight, you will have a little bit of time tomorrow in class. And I'm sorry for it being 2 pages. Somebody messed with my stuff. I'll find out who it is, and they will be sorry. I'll do that for you, just for you. I know, right? Someone. But if there aren't any questions, you have the rest of the period's work.